In the previous video, we talked about Gauss' theorem, which connects volume integrals with closed surface integrals. Here, we will cover Stokes' theorem, which instead will connect surface integrals with closed line integrals. We will start in 2D and derive the equations. This will also be called Greens' theorem. Start by drawing a closed curve in the xy plane. This curve will, for simplicity, be a small rectangle. Call the size of this rectangle delta x in the x direction and delta y in the y direction. Define the position of the first corners x and y, which gives the following coordinates for all corners. Then call the area of the rectangle A, which is given by delta x multiplied by delta y. We will also call the closed curve, which is the blue line, the boundary of A. Now, we can define the circulation gamma, which is the closed line integral of a vector field v around the curve. The mathematical definition states that we should integrate counterclockwise, which gives the following line elements. We also call the four lines L1 to L4. This means that we can write the integral for the circulation as four separate integrals, each over a straight line. Let us start by looking at the first line. We can write the line element as s hat ds. Then we can identify s hat as x hat for the first line, which means that v dot s hat will be the x component of v. The position vector should be any value on the line. Use x and y as it's easiest. We can now assume that Vx is approximately constant and approximate the integral by Vx times the length delta x. Let us move to line 2. ds is in the y hat direction, which means that v dot s hat is the y component of v. The position should be on the line. Pick the lower coordinate as it gives the easiest equations. Approximate the integral as vy times the length delta y. Continue to line 3. ds is in the minus x hat direction, which means that v dot s hat is minus the x component of v. As we pick the left position for L1, pick the left position here as well. Approximate the integral as Vx times the length delta x. Finally, line 4. ds is in the minus y hat direction, which means that v dot s hat is minus the y component of v. As we pick the lower position for L2, pick the lower position again. Approximate the integral as vy times delta y. As our next step, we can collect these terms, which are in the x direction, and collect the y direction terms. Multiply and divide by delta x, and identify as the partial derivative with respect to x. Multiply and divide by delta y, and identify as the partial derivative with respect to y. Both terms now contain the area delta x delta y. If our rectangle is small, the partial derivatives will approximately be constant. Then, we could instead of writing the expression as integral over the area. This is the relationship between a closed curve integral and the area integral in 2D. However, we have only shown it for a very small rectangle. What happens if we connect two rectangles to each other? If you watch the Gauss theorem derivation, this will be very similar. When we add the two closed curves together, can we still claim that the equation is valid? Start by looking at area integral. We know that the area integral, the total area, should be the same as the sum of the area integrals of the two rectangles added together. This works fine. It is a little bit more complicated for the line integral. Is the total line integral the same as both added together? The combined line integral over the boundary will be this orange rectangle. This means that the connecting lines between them are not included in the combined integral. However, as we integrate the line going to the left for the upper part and along the same line going to the right for the lower rectangle, we cover the same line two times, but in opposite directions. Hence, these two will cancel each other, and we can still claim that the combined integral is the sum of the two individual ones. If we add a third rectangle, we will again have the two connecting regions. Here we have one integral going up and the second one going down. And the two will cancel each other, and the expression is still valid. Now, the closed line integral will be this orange curve. This means that if we extend the region with an extra rectangle, the expression will still be true. Let's say that we want to have a circular region. We cannot fill it with small rectangles. And then let the number of rectangles go to infinity. And we can now see that the area of the blue rectangles become the area of the circle. We can also see that the boundary of the rectangles is close to the boundary of the circle. And we say that the equation is valid for any simply connected region in 2D. But what if we leave 2D and assume that we have a curve in three-dimensional space? The orange curve is no longer a good approximation to the red curve. We need to add something more to handle curves in 3D, which no longer are restricted to a single plane. Our first step is to change from the area integral to our surface integral we use in 3D. Hence, call it S instead. Let us go back to our small rectangles again, but this time assume that they are three-dimensional. Let's add two small rectangles in the xy plane. We know that the connecting line between them, marked in red in the figure, cancel each other. Now let us change the direction of one of the two rectangles. Note that even if we change the direction of the surface, the line integral between them in the connected region still cancel each other, as we integrate in one direction and then the same integral in the opposite direction. As our original equation was derived in 2D, we can say that it is valid for surfaces in the xy plane. By symmetry, we can get similar expressions for the other two planes by doing cyclic permutations of the coordinates. Hence, we get the following for the YZ plane, which is the current direction of the blue rectangle. We also get the expression for the XZ plane. Now, let us recall the expression for the curl of V. We can see that the Z component of the curl is the same as we have in the equation for the xy plane. Hence, we can replace it with Z hat dot the curl. The X component has the same expression as the YZ plane, replace it with X hat dot the curl. And the Y component corresponds to the XZ plane, replace it with Y hat dot the curl. Now, we can draw the normal vector of the green surface in the xy plane, which is z hat. Hence, replace with the normal vector. The normal vector for the yz plane is x hat. Hence, we can insert the normal vector in the equation again. Let's add a third rectangle. Let it start in the xy plane where the normal vector is pointing up. The direction of the normal vector should be continuous, which means that here it should have the same direction as its neighbors. Then, when we turn it to the xz plane, we get the direction of the normal vector. This time, the normal vector is y hat, and we can again insert n hat in the equation. Finally, the x times dy is just the surface element ds. dy times the z in this equation is also the surface element ds, and the x times the z is the surface element in the final equation. And we can see that for all planes, we ended up with the same equation when it is expressed in terms of the curve. At this point, we have shown that our expression works for all surfaces that are aligned to one of the three planes. You can probably guess that it will work for other directions as well, but let's be a bit more structured. Note that the combined surface of these three elements will have a closed curve integral according to the orange curve. This curve is no longer restricted to a single plane. Let's go back to our previous example where we had the bottom surface, here with normal vector pointing up. What we want is to have the red curve as boundary. What we can do now is to add vertical elements in the yz and in the xz planes to reach the red curve. These will have normal vectors pointing inward to match the normal vector of the bottom region. Now, add vertical elements all around the surface, which gives the new boundary as the orange curve. Then, if we let the number of elements go to infinity, we get that the orange boundary approximates the red curve. The orange spikes you see are drawing errors of the graphics engine and can be ignored. If you are mathematically strict, you could claim that there is a problem in that while the position of the orange curve is the same as the red boundary, its length is different as we only move in one direction at a time. Hence, the orange curve will be longer than the red curve. However, if we look at the line element ds, which in 2D consists of one step in x and one step in y, we can see that if we first integrate along x, the integral is approximately v dot dx x hat, or vx dx. If we integrate along the y direction, we get the contribution vy dy. This means that combined, these two gives the following. However, we can write this as v dot dx x hat plus dy y hat. And this is the same as taking dot product with ds. This means that as long as v can be considered as a constant, taking one step in x, then one step in y, is the same as directly taking one step in ds. As the orange and red curves occupy the same position, we can consider v constant at the corresponding positions. Hence, only taking steps in the three directions give the same integral as moving along the red curve. Therefore, our equation is still correct. Note that the derivation for Gauss' theorem in the previous video had the same issue. I just chose to ignore it that time. The conclusion is that the line integral over the boundary is the same as our integral for our surface in the three planes. But what if we have another surface with the same boundary? The green surface will now have normal vectors in different directions. Let us call our new surface S1 and the previous blue surface S2. We know that the equation is true for the blue S2. Let us calculate the difference between the two surface integrals. We can move the minus sign to the normal vector, which then changes its direction. As the negative normal is pointing outwards, we can note that this is now a closed surface integral over the combined surface. For a closed surface, we can apply Gauss' theorem and rewrite it as a volume integral over the divergence. If you remember our vector identities, the divergence of a curl is strictly equal to 0, and the integral is 0. We therefore have that the difference between the two surface integrals is 0, which means that the two integrals are equal. This means that all surfaces which has the red curve as boundary will have the same surface integral when we integrate the curl of a vector field over the surface. This is a consequence of that the rotation is a divergence-free vector field. With this, we will conclude the derivation of Stokes' theorem and finally claim that this is an equality. Let us demonstrate Stokes' theorem with an example, which will be the rotating flow we had in the video about curl. We had a constant curl inside the circular radius r and 0 curl outside. The goal is to calculate the tangential velocity v5. Let us first draw the region with curl omega 0. Then add the closed curve in blue that we'll use in Stokes' theorem. The curve has radius r and moves counterclockwise. We can now rewrite the closed line integral by noting that v dot s hat is the tangential velocity. Due to symmetry, we can assume that the tangential velocity only varies with the radius, and hence is constant in the integral. We can simply multiply with the curve length 2 pi r. Start with the case r is smaller than the curl region for the surface integral. The curl is the constant omega 0. N hat for the surface is z hat, and the dot product is just 1. We are integrating a constant over surface, hence multiply with the area of the surface pi r squared. Divide by pi r. And we get our expression for the tangential velocity. The second case is when r is larger than the curl region. Insert a constant as curl, but limit the integral to end at the full radius of the curl region. N hat dot z hat is 1. The surface integral is a constant times the area of the curl region. And we can solve for the tangential velocity. This gives the following solution as we saw in the curl video. I want to make a quick comment about simply connected regions. Let's say we delete the curl region from the domain. Is Stokes' theorem still valid? The integral over the boundary is still the same, but we no longer have any curl on the surface. Hence, this is not valid. And the conclusion is that we need simply connected surfaces for Stokes' theorem to be valid. Then the question is, what can we do if we have a hole in the domain? A classic case is to define a closed boundary as the blue curve We will make one circle in one direction, then move into the hole and make a circle in the opposite direction. The region inside the blue curve is now simply connected, as the hole is outside the curve, and Stokes is valid. Let's make the gap when we move between the two curves smaller and let it approach 0. Here we are moving in one direction along the integral and then in the opposite direction at the same position. Hence, the contribution from this part will cancel. What we basically have now is our two closed curves, called outer one C outer and inner one C inner. We can now say that the sum of the closed curve integrals of these two will be the surface integral of the curve, over the region between them. Note that the two curves move in different directions. This is a classic trick of handling non-simply connected domains by isolating the missing regions. A similar idea would work even if you have multiple regions missing from the domain. Finally, I will just mention that there are other versions of Stokes' theorem as well. One is if you have a line integral with a cross product instead of a dot product, which gives the following. There's also one version for scalar functions. You ever take the cross product with a gradient in the surface integral. As these are not as common though, it will be enough to know that they exist here. This is the end in this part about integrals in multivariable calculus. We will talk more about integrals in the videos on cylindrical and spherical coordinate systems though. Thank you.